Good morning, everyone. Am I audible to you? Okay, thank you. Okay, today we will start a new topic. Okay, yes, the last class we have discussed about the ILD of different beams. So today we will start a new topic, moment distribution method. I think all of you have already got this in your previous semester. Is it moment distribution method? Have you heard this term before? Okay, so we'll start that moment distribution as you have already got this in your previous semester. So you have an idea about what is moment distribution method and what is this. Still, we will go through once. So as you can see here, this is a moment distribution method introduction part. We will discuss about little bit about this. Then after the introduction part, we will going to solve some numerical and all. So all of you please go through this PDF. So there are some definition and some introduction part is given to this. So as you can see here, moment distribution is an iterative method of solving an indeterminate structure. Okay, and this method was first introduced by Hardy Cross in 1932. Okay, so moment distribution is suitable for analysis of all types of indeterminate beams and rigid frames. It is also called a relaxation method, and it consists of successive approximations using a series of cycles, each converging towards final result. So it is comparatively easier than slope deflection method. This is another type of method. We will discuss about this after yeah, in the next topic, slope deflection method, Carnage method. There are so many methods similar to this moment distribution method, but moment distribution method is the simplest or easiest method among all these things. Okay. So it involves solving number of simultaneous equations with several unknowns, but in this method does not involve any simultaneous equation. These are the some introduction things. All of you please go through this. I will share this PDF with you. So the primary concept of this method is what we need to find out friction moment, then relative or beam stiffness or stiffness factor, distribution factor, carryover moment or carryover factor. I think all of you have heard these things. Still, we will discuss about this. What is this? So, what is the basic concept of this method? In moment distribution method, counterclockwise beam and moments are taken as positive. The counterclockwise beam and moments produce clockwise moment on the joint, and we are using the sign as anti-clockwise is positive and clockwise as negative. Okay, so there are some assumption of this method. What are the assumptions? These are the very important points. All of you need to remember this. What are the assumption of moment distribution method? You may get questions in the exam. Write down about the assumptions of moment distribution method. So you have to go through this. So these are the some assumptions. What are those? The first is all the members of the structures are assumed to be fixed, and peaks and moments due to external loads are obtained. So, what is this? According to this assumption, what we need to do, we need to assume all the support to be as fixed. If there is hinge, roller, every something is given, but we need to assume that also as fixed support. Okay. So all the hinge joints are released by applying an equal and opposite moment. This is the second assumption. The third assumption that the joints are allowed to deflect one after the other by releasing them successively. The unbalanced moment at the joint is shared by the members connected to the joint when it is released. The unbalanced moment at the joint is distributed in the two spans with their distribution factor. We will discuss about this. What is the distribution factor? The Hardy-Cross method makes use of the ability of needed structural members at a joint to sustain moments in proportional to their relative stiffness. Okay, so there are some formula of friction. So all members of a given frame are initially assumed fixed at both ends. The loads acting on this fixed beam produce friction moment at the ends. Friction moments are moments exerted by support on the beam ends. These moments keep the rotation at the ends of each member zero. Okay, there are some As per the loading, as you can see here, there is some loading is given, point load. See, in this there is a point load, and also in here there is a point load, but there is a difference. Okay, this point load is applied at the middle of the beam, so the formula is something different, and here it is not provided at the middle, so the formula is different. Okay, here also point load is there, but the end friction moments are different as per the loading and as per the support. These are some how it look like when the load is given at different distance, how it look like. It is given some example of that. So what is the stiffness factor means? The definition is given: when a structural member of uniform section is subjected to a moment at one end, then the moment required so as to rotate that end to produce unit slope is called the stiffness of the member. Okay. So what is this actually? So basically, if we apply a moment at the support of any beam, so to resist that moment, another moment is generated against it, and that is nothing but this call is stiffness of that member. Okay. So stiffness is the member of force required to produce unit deflection. It is also the moment required to produce unit rotation at a specified joint in a beam or a structure. It can be extended to denote the torque needed to produce unit twist. So there are some formula how to find out the stiffness factor. So beam is hinged or simply supported at both ends, then we need to use this K equal to 3ai by L. If the beam is hinged or simply supported at one end and fixed at other end, then we need to use this K equal 4ai by L. Okay, these are the formulas given as per the condition. So all of you know what is E, I, and L. E is nothing but Young's modulus of the beam. I is moment of inertia, and L is the beam length or beam span. Okay. So and after this, there is another one important term is distribution factor. So what is the distribution factor? When several members meet at a joint and a moment is applied at the joint to produce rotation, without translation of the members, the moment is distributed among all the members meeting at the joint proportionate to their stiffness. So this is called distribution factor. Let me show you one another. This is the handwritten notes I have already given to you. All of you please go through this. The same things is given here. What is the carryover factor, carryover stiffness, and this thing. So distribution factor. This is distribution factor. See, there is a point O and there are four members connected to this. So if we distribute all the moment among these members, this is called distributed. Okay, distribution member. Yes, and how we need to distribute that amount is called distributed factor. Okay, so there is an expression for distribution factor. As you can see here, this is a frame where four members are connected: OA, OB, OC, and OD. If we consider a moment M applied at the joint O, all the members rotate by a same angle theta, then this moment is given by M1, M2, M3, M4, which is nothing but the total moment M. It is distributed among all the members. Similarly, if we need to find the stiffness, what is the deflection, then also we need to use this formula: theta is equal to this. Finally, what is distribution factor? Distribution factor is given by Mi by M. Okay. When we solve the numerical, you will easily understand this, how we need to consider this distribution factor. Okay. This is distribution factor. If there is three members, as you can see here, one is K1 by K1 plus K2 K3. Similarly, K2 by K1 plus K2, K3, and so on. Okay, as per the members, we need to find out like this. Okay, so this is nothing but relative stiffness by the sum of relative stiffness at the joint. Okay, next is carryover moment. What is this carryover moment? It is defined as the moment induced at the fixed end of the beam by the action of a moment applied at the other end, which is hinged. Carryover moment is the same nature of the applied moment. It will be clear when we solve a numerical, don't worry about that. So let's see one example. It is a beam given. So how we need to find out the distribution factor for this type of beam? As you can see here, there are four joint A, B, C, D. So you need to consider all the members connected to this. From joint A, what is the member connected? It is AB. So in B, it is BA and BC. In C, it is CB and CD. And in D, it is DC. As per that, and as per the condition, we need to consider the relative stiffness, these values. Okay. So sum of the relative stiffness, and always remember the distribution factor in every joint. In every joint, distribution factor is how many members are connected, it doesn't matter, but if we add all the members, it will always come up as 1. Remember that. As you can see here, the first part, it is only one member, so it is come out 1. In the second joint B, there's two members connected, but when we add up this 3 by 7 and 4 by 7, you will also get 1. Similarly for C and for D. Okay, so these are the some example how we need to find out this distribution factor and all these things. For fixed and it is different, for free and it is different. So remember that only the difference is there. Okay, as here you see the moment of inertia is given different for the both the span AB and BC. So as per that we are considering this 3I and I. Okay, this is the simple things. I will give this PDF to you. All of you please go through that. Also the notes are given in this also. So in the next class what we'll do, we'll discuss a numerical. Okay, this numerical we'll discuss. Today we'll not start the numerical as it is long, we will not able to finish this today, so we'll start it in the next class. So all of you please go through the theory parts, the introduction part once before going to the numerical. So we'll start this numerical in the next class. We'll not start today because it is a long one. We'll not able to finish it today. So you do one thing, all of you please go through the introduction part, okay? Before going to the numerical, all of you please go through the introduction part. Okay, when you got this in moment distribution in the last, in third sem or fourth sem? Okay, in fourth semester, no? Okay, fine. So I think all of you have a little bit idea about this. So still, there may be little something, some part may be different. So all of you please go through the theory part, okay? Once after, if you understand once the theory part, then we can easily go to the numerical and we will discuss about that in the next class, okay? So is there anyone have any doubt? You can ask me, or you all of you please give your attendance in the chat box also. In the meanwhile, I am marking your attendance. Okay. Okay, is there anyone left to give your attendance? All of you are present here. Integrated, everyone is present. Okay, then everyone will continue in the next class. The new paper. All of you please go through this introduction part. We'll start a new vehicle in the next class. Okay, thank you all.